So the first session here this morning is part two of our computational challenges for MMA. And kicking us off is Colin Slater from University of Washington to talk about squeezing every last picture from the sky.
Every picture is right. That's exactly right. Hi, I'm Colin Slater. Work as part of Rubin data management team on processing all the data that we're taking. So this talk is going to be a bit of a sort of lightning introduction to like how we think about processing the data, and then like straight into what challenges we're facing like at this moment at our current stage of the survey. So we kind of touched on it in many other talks already, but just to kind of lay down a little bit of the basics, the Rubin Observatory, the key feature is this 3 gigapixel camera, and it's the observatory's whole goal is to take images all night, surveying the entire southern hemisphere sky. The idea is that we do a sort of a mostly uniform survey to get to provide as much data as possible to satisfy a wide variety of science cases for our users. Um, so yeah, a lot of this talk will be really about like where we are at this very moment. And so we went on Sky with the observatory a little over a year ago. And since then, we've been in the commissioning process of solving all of the bugs that happen when you put a new camera on the sky in a new observatory. We've been dealing with all the features in the data that we need to handle, and ramping up our ability to keep up with the data. And then right now we're at the phase where the collected volume over the past years is really that volume is now becoming a challenge. Like we've reached the phase where dealing with the sum total of all this data is really the challenge for us. So that's what we're going to get into in a little bit. So a little bit of context also related to the various MMA talks we heard earlier. So there's two different flavors, like broad categories of data products that Rubin is providing. So yesterday we heard a lot about like timely prompt things, like we were observing during the night, we're sending out alert stream, and the various brokers and downstream systems are listening to that alert stream to be able to go follow up on supernovae or gravitational wave events or anything like that. We call that the prompt data products, or the alert stream, or prompt processing. That's all the flavor of science products that we're making available during the night. But a part we didn't hear much about yesterday was what we do with this total sum total of collected data, which is that annually we reprocess the entire thing, every single image that we took, to give us our best understanding of that data. So there's things that we can't do in 60 seconds. There's things that we can do better by waiting for an entire year of observing to better calibrate the data. I'll talk more about what we're doing here, but so I'm mostly going to be talking about this data release process that happens on a kind of annual cadence rather than the in the night cadence. So, like I was saying, our goal is to give the best view of this data for the science users so they can get the most out of it. And that means we're like the basic outline of that. This is like a super simplified schematic, but it gives you like the high level like stages of the processing that we go through in order to build these data products. Is that we need to calibrate every image. And by doing this every year, we get our best available calibration to make sure we get that really solid. We then stack all of these images. So we're taking hundreds and hundreds of images per night. Most of those are sort of going all over the sky, but every few nights we're coming back to the same point on the sky, and we're getting more and more images that cover any given galaxy or star or object in the sky. And so we're combining those images from multiple nights, from multiple images of all those objects to get both more precise measurements of those objects and to find fainter objects that you can't see in just a single visit. So that stacking process is a bit of there's like a shuffle operation there where we need to take all the images that could, like the images were taken all over the sky. We need to find the ones that correspond to a particular spot, combine those, and then we measure on those. That gives us our best measurement for people who are doing galaxy science, people who are doing Milky Way science, people who are doing cosmology. They want our most precise measurement of like all of these galaxies. And that's what they get here. And then we also go back and measure the entire history of those objects through all the images that we've taken. This is for people who want sort of the historical, like the light curves, history of the object, but they don't need it in necessarily a like night by night form. So clearly I've drawn a directed acyclic graph up there. That's clearly how we think about the processing. We build giant DAGs and run them. So a key part of the way we built the pipelines is that we separate out this DAG building structure from the actual work itself. So all of our algorithmic developers who are thinking about what's the best way to calibrate this, what's the best way to measure this, they are purely thinking about a piece of Python that declares its inputs and declares its outputs. It says, I want to read the calibrated image, doesn't know where the calibrated image comes from. It just is presented with that calibrated image. The algorithmic developers can do their thing, figuring out how to do that, write out some outputs, but then they don't have to think about how these pieces get put together. We separate that into a different piece of middleware code that says, okay, this thing is producing this output, and this other task needs this input. I can put those together. So we really separate the concerns here in a way which I think is super productive. We also abstract the I/O away from all of this. So our algorithmic developers, again, don't have to think about, how do I read this file? How do I serialize this? What's the data format going to be? That's all handled by a different component that we call the data butler. And its sole responsibility is keeping track of all the files that are created as part of the processing. It presents those Python objects, it does the deserialization to the algorithmic code in, say, the calibration task. And then it also receives the outputs. And it's both talking to a storage backend, which we have numerous different storage backends because it's all pluggable because the only interface is through this butler. And it also talks to this database, which stores our knowledge of every single file that all of our processing creates. So this again does a nice separation of concerns between like the processing details and the algorithmic details. So there's like a lot of implications of this structure that like sometimes you can actually miss it. I like didn't realize all of these until I sat down and kind of wrote out the slide that because this task is really like our level of granularity for the algorithms, it also means that it's the level of granularity for our scheduling and our parallelism. So we don't generally need to do like big multi-core jobs for parallelism. We have tons and tons and tons of images. So we have way more images than we have CPU cores. We just throw those images all as single core jobs to get parallelism. Makes it a lot easier for the developers to deal with. It also means that that's the level of granularity for our data storage. So any one file can only be written by one task. And so each task has to write out its result at the level of granularity that it was run at. So for calibration tasks, that might be like one detector on an image, or any of the image processing tasks might be that way. Another cool thing that I didn't think about until someone mentioned it today was that this is also our level of granularity for monitoring. So like I mentioned, I'll mention in a minute that this is all going to HTCondor. That means that HTCondor is going to provide statistics for us at this level of granularity. So when I'm trying to understand like what is the performance bottleneck in some long chain of pipelines, we get straight from HTCondor the all of the monitoring at this level of granularity that we can say, oh, it's the calibration that's taking long versus it's the measurement that's taking too long. So this is just the super quick version of what happens from here. This is Greg Dawes is going to talk more about this in the next session about the details of how we actually get these jobs onto the cluster and run them. But at a high level, we have some Rubin specific code that's sitting at the top of the stack. The user only interacts with that. That then generates it builds its view of the DAG based on the data that exists and what the user is requesting to be processed. It generates a giant DAG that it passes to DAGman and HTCondor. We don't actually have bare metal HTCondor. We have all of our clusters. We rely on glidins on top of a cluster provided by the infrastructure providers. This works really well. We're all like really pleased how well that works. And then that lands on the actual compute nodes. So okay, to get into the what's difficult part, since that was part of the charge for this talk. So we're just now coming out of a phase of processing kind of a preview data release of a bunch of the commissioning data that was taken over the past year. Past year has been a mix of engineering and sort of science-like data taking. And I pulled up some numbers on what this looks like. It's 30,000 images, 3 million core hours. The input data volumes, like these data volumes don't super scare me. But along the way, we generated 7 petabytes of intermediates and over 100 million files. I didn't count. Once we got to 100 million, I thought, okay, that's enough. So okay, now that's getting a little worrisome. So I said processing all the images. We're about to start this the sort of full mode of survey operations where we're not doing engineering, we're just surveying the sky. And once we've done a year of that, we're going to be doing a data release that processes all those images. That's going to be about 5 times bigger than what we just did, getting closer to a petabyte of inputs, well over a petabyte of outputs. And if I just naively do the math, that runs up to 47 petabytes of intermediate data products. Uh, that's going to be a problem. That has me really worried. So, and that's just the first year of data taking. Every year, we're going to process the entire data set from scratch. And so every year is going to get harder and harder and harder. And so we're going to have to get better and better and better at handling this. So, okay, so this is something that's like true. If you asked me today, I wouldn't have given this talk a year ago. I wouldn't have, I'm hoping I won't have to talk about this so much in a year from now, but right now, storage is really difficult. All of our tasks write their inputs and outputs to storage, and that's really convenient for getting the pipelines off the ground, but it's clearly going to become a scaling issue. We filled up our 30 petabyte storage cluster, and it turns out that it's way harder to recover from that than I would have guessed. Like you think, oh, I'll just delete some petabytes of data, and it turns out that nobody like builds a complicated storage system that's optimized for deletions. Like that's not a selling point. Um, so it took like over a week to like get anything going again. So we really got to be on the lookout for that in the future. Um, so that data release, we're also going to be processing at multiple different sites. So this is our way of scaling out to get more compute resources. Slack, which the 4 sites are Slack, INTP3, RAL, and Lancaster. We're right now running HTCondor jobs at all of those sites using our centralized access point at Slack. This is very cool. I'm very happy about this. So the process, the compute side is looking pretty good. We're still going to have challenges with the storage side because now, like, we can mostly say, okay, you go process this side of the sky, and we'll go process that side of the sky. But we're going to need to move data back and forth just for debugging or because one site goes down or something like that. And that's really a bottleneck for us right now. So. This is really my last slide is to land on a few opening questions where I'd really love to hear like what other experiments have how they've grappled with this. How do people think about these problems? Um, we're going to have this distributed processing, and that brings the question of like, do we need to centralize our knowledge of where the data are? So we have like one source of truth for that tells us where everything is, or do we decentralize so that each site can operate independently so that we're not running into scaling issues? Um, there's hard trade-offs there. Um, we're trying to figure out how to deal with the trade-off between having really granular data access versus the bookkeeping costs of having hundreds of millions of files. Like you kind of, we're going to have to implement something either way. Like either we implement bookkeeping of tons of files or we implement layers that coalesce files and allow you to sort of slice individual pieces of data out of those files to run on tasks. Either one of those is work. So I'd love to hear more about what people have, like how people have tackled that type of problem in the past. Um, we're yeah, we also need to like we're mostly because I said we're like partitioning up the sky for the most part. That mostly means that we can pre-stage at least the raw data that's going into this processing at the different sites. But you can imagine that we might also want a capability to say, I'm sending this job to IN2P3, wherever the data is, just get it there for that job. That kind of just-in-time mechanism. Uh, I can see value there. I don't like, do we want to rely always on just-in-time data delivery? Again, there's trade-offs here. Would love to hear how other people have dealt with questions like this. And overall, just like the best way to like deal with a lot of these problems would be to avoid the problems of having so much data to store. Clearly, we have to store the inputs and the outputs, but if we can find ways to reduce the intermediate burden on the storage system, I think that would be a nice way to avoid a lot of this. Um, so that's basically where I'm going to end. I will say though that just for on a fun note, Rubin Observatory, a lot of people, like so many people have contributed to getting Rubin Observatory to where we are today. And that actually includes HTCondor. So I don't know if everybody knows this, but when we had our like big press release back last June, all of those images that came out of that were processed by HTCondor. So HTCondor is a key part of Rubin as well. So thanks.
Okay. Questions? I see a few. So that hand first, then Frank will be second.
So you didn't actually mention Rusio specifically, but I know that Rubin is using Rusio. Uh, and Rusio is certainly capable of doing some of the things that you're talking about in your last slide of challenges.
Yeah, we are using Rusio right now. I think we are pushing the limits of Rusio right now and figuring out exactly how far we can push it. And that's really like a topic that we're like working on absolutely this week.
Well, I mean, I know that some of your Rusio people or some of Dune's Rusio people, we have people working on this same project. So there's shared knowledge there. We need to make sure that's communicated. Actually, I should congratulate you on shoving half of the universe into less data space than what Dune is using for a few number of neutrinos. So we have more size of data, but fewer files at this point.
Yep, Frank.
So there's probably a half a dozen to a dozen people in this room who've dealt with problems very similar to yours, and there's probably as many opinions how to deal with it. So let me add one opinion of how to deal with this. My piece of advice would be to depend on 90% of what you have to do above, basically default into pre-staging, but have the ability to do on demand so that you can deal with the edges. And then ask yourself if there are some things that are so compute intensive, so slow, in other words, that it's not worth moving the data at all, and you just access the data from remote. And then the last comment is, I understood that that you have a structure fundamentally that is hierarchical in the following sense, that you're sitting on a piece of equipment, a node, piece of hardware, and that your glide-in a priori can either control a single core or control many cores. And so you have the ability to, in principle, package the files for many tasks in order to deliver them into your environment at once. And given that a node these days, or at least soon, has between 256 cores or 512 threads, there is a factor 100 in number of files to manage. And so I would encourage you to think in this hierarchical way, so that while you have all of these files individually, you might want to zip them up, deliver them into your environment, unzip them, and therefore have in movement, when you're managing movement, 100 times fewer files to manage than you are when you are actually in processing by the tasks. Am I making sense?
Yeah, totally. That I see exactly where in the graph that you're like describing this operation. That's yeah, I'm gonna have to go think about that. I'll just throw out that like the one difficulty that we have here is that right now our level of granularity is at the detector level, and the next natural step up is the entire focal plane, which is a factor of 189. And so it'd be really nice to be able to step up by 2, 4, 6, 8 instead of 189. But we can probably come up with some ways to like invent parts of the partial focal planes
and it's
like
really
that to make that happen.
I think that Butler should know all files, but when you're actually moving from Butler to the execution environment, it might be worthwhile to temporarily have a smaller number.
Yeah.
By about a factor 10, 100 or so.
So,
Thanks.
Colin, thank you for it, especially for the last slide of all these images were processed by Condor. You're now joining the DreamWork with all their movies since 2011, processed under the control of Condor. But looking at your numbers, you have the input, you have the output, which are relatively small compared to the intermediate. So how can we better understand the flow of the intermediate? I assume that this is part of the input of some of the transformation downstream. And do you keep them? Do you care about them? Or once you use them, you throw them away? What is the life story of the 40? You had 47 peta of intermediate. Is that you write them to dev null or?
So the quick version of that is that this shuffle operation here, we basically write copies of like this edge, and that's one file. This edge, that's a file. Like all of these edges become files, and we do that to disk because that was sort of the natural framework that we had, and it scaled well until the point where we have
But
Your
once I
LCD
did it, can I throw it away, or you want to keep it, or
we like really,
you know, what is the provenance of all this? And because it's not the output, but it is an output.
it's extremely handy to keep around if we need to rerun this stage here, but it's not essential. So there's a bit of time-space trade-off there where
Right.
we can always regenerate them at the cost of more
So-
time if we need to go back there. So far we haven't done that. Like some of this is just like things that we should do and just haven't done.
So it would be useful moving forward to figure out where do you have the control knobs to decide what do you do with the 47 compared to, I think you had only 1.5 of output. So you had an order of magnitude more intermediate than output. So that may be a significant part of your storage challenges.
Yep.
Thank you.
True.
All right, let's thank Colin again.